So this paper is very simple. In fact, it is only to compare modeling results from different models to gain confidence for, especially it's a collaboration with SAMI, and I will explain that SAMI is very comfortable with some models, and now they want to get the confidence to use MHD-Valdis to investigate stability, while they are currently using other software for computing the magnetic field and the current density. So I will, in the introduction, I will present the model that were presented by SAMI for their retrofit work, and then I will then present modeling results obtained by MHD-Valdis for the magnetic field, and then I will do this similar comparison with the current density produced by ANSYS thermoelectric done by SAMI, and then some produced by my own work. So this is the modeling result, the model itself, and the model result presented by SAMI at TMS in 2024 for the retrofit study of a cell operating at 330 kiloamps, and then retrofitted to operate at 350. So they changed the bus bar, they changed the lining to be able to increase the amperage. So this is the part of the ANSYS model is the conductor. ANSYS is finite elements. I will explain next slide what it invokes. And then this is the vertical component of the magnetic field that they have obtained. That is a very good one, of course. But the point is that can they trust to get the same result with MHD-Valdis for the magnetic field and for the current density. So using ANSYS to compute the magnetic field is not new. I was the first to do this kind of model. After that, at the request of Alcan, ANSYS company added a finite element formulation for magnetic field that we can use for computing magnetic field in cell. So in 1994, I presented this kind of model that is quite good. So that's been used very commonly in many companies and many institutes, by Alt Institute in China. The point is that it's required to mesh the air around the pot to compute the magnetization effect of the pot shell and get the magnetic field inside the cell. So that's implied construction of geometry and CPU time. And also, well, it's a magnetic field that is not available for computing cell stability. So that's convenient to use the same code to compute the magnetic field, the current density, to obtain the Lorentz force, and then to trigger the stability analysis. And the second model that the SAMI presented is the ANSYS-based thermoelectric to obtain the cell balance, the ledge profile, and also the horizontal current in the metal band. So this is in their work. They have improved reduced the horizontal current from the initial design to the new design. And so again, they are feeling very confident with using that model. So the idea is, okay, is using MHD-Valdis getting the same result? And that's the point of this paper. So MHD-Valdis the main purpose is to analyze the stability, but the ingredient is the magnetic field and the current density. So it needs to be computed. So it must be computed accurately so that you get confidence that your stability analysis is relevant. So I will start with the magnetic field because it go in the same order of the paper from SAMI. You compute the magnetic field, you need the source course current, but I'm going to get them next when I compute the electric network. but I'm presenting magnetic field first. So to compute the magnetic field in image device, this only thing you need to do is to mesh the ferromagnetic element. So you have to create the geometry of the ferromagnetic. You have to have the conductor that is done by the electric problem. Once you have both, then you solve without having the need to measure the air, because the air is not required for this formulation. That is boundary element formulation, and you get quicker the magnetic field than ANSYS. And you, as I'm presenting here the result for the same problem, I'm getting using image devices a very, very similar magnetic field than they presented in their paper. So this is the first confirmation that the two models are solving essentially the problem and computing the same magnetic field. Okay, then the first step for MHD values is to compute the electrical network to get the current, and as part of that you get also the current density and the metal pad. And then so you need to create the geometry of the bus bar, and this is fairly well. This is the task that is more difficult to learn, let's say. And once you have learned how to do this, then you get very quickly you get the current density in the metal pad, and then I will compare with what they have published with ANSYS later at the end of the paper. But first, I want to introduce even more modeling comparison. So this is the one obtained with image values. You can obtain something the same using ANSYS, but a different type of a model in ANSYS. This one is a full 3D. It's parametric, so you can create the geometry for very quickly for any cell design. And then you compute the current density in the metal pad in 3D. And this is the solution that I obtained with this model that is electric only. The next one is ANSYS thermoelectric, same style of model that Sami is using, but this one is my own version. And so I created the model using the same geometry, and I obtained this current density in the y direction. That is the only one direction you are getting the horizontal current, because you're not getting the x direction in that slice model. And the x direction is important, by the way, so it is like this morning in the previous session when introducing different bar to have different resistivity, that was creating a horizontal current in the x direction. Okay, the last model that I will compare with the model, the result presented by Sami is a very simple Excel worksheet that I have developed for LChem China, because LChem China is using this kind of model to compute the horizontal current and see cathode voltage drop for their prototypes where they're super paste. We will see a presentation about this this afternoon. Okay, so this is you simply input the input parameter here, and you get the solution for the horizontal current, and you get the CVD in Excel. Okay, and then now that I have done all those models, then I will present the comparison. So this is the horizontal current with all my four models. So as you can see, I'm getting essentially the same solution, and that can be compared with what Sami has obtained for after the retrofit. So essentially, all five models are in agreement. So this is the issue is then after this comparison, I guess we can feel confident to use those two fields, the magnetic field and the current density field, to compute a Lorentz force and then to calculate a flow. And so that's what ImageD this is doing next. So you have the steady state solution using the 2D shallow water approach. That is also very quick to calculate. SAMI, essentially, at that stage, they will use CFX and solve in 3D flow. And they have not presented those results TMS, and when I ask for those results to add to this paper, they say it's not available. So that means they have not even done that calculation for that project. They felt confident to go straight to implementation only with the magnetic field in the JY, the improvement of the horizontal current. And so you get also the deformation of the bat metal interface. You also solve the bat flow, but it's required to compute the deformation of the interface. But typically, we are not showing that result unless we are studying alumina dissolution simulation. Okay, and then the last thing that MHD Valdez is doing, that is the most important for people studying stability, is to run transient and then to get from that a damping rate for the wave. And at this point, it's important to quote the friction factor that you use in your model to get this damping. And here I use the 0.02 friction that is quite low, and still I get a very stable prediction. And the only way to be sure that you're fairly close to reality is to do a squeeze test like we have seen to see that to compare the prediction of a model like MHD Valdez with observed stability, and then you calibrate that number, that friction factor, to reproduce the measurement. So the conclusion is that it was fairly easy for me to reproduce what SAMI have done for their retrofit, and so that they get confidence and you get confidence in general to use MHD Valdez to do cell stability. And well, I could have been wrong, and then here I'm quoting the reason why I could have been a discrepancy in the result. In the electrical network, you could no, that's just magnetic field. You have to represent 3D busbar by 1D elements, so there's a kind of a learning curve to do this properly. You have a pH curve for the magnetization that could be different than the one they have used, so that was not in. And then there's a setup for the boundary condition for the convection and radiation on the bus bar to obtain the right temperature. They could have done this differently than I did. So, but so if I would have seen a discrepancy, I would have investigated those things, but it was not required. Same thing for the current density. There's a lot of reason for possible discrepancy. The way you handle the contact resistance, the choice of temperature if you're using only a thermal an electric model, like one of my model was, and some property. But again, it was not required to investigate. So, considering this, I think SAMI can feel more confident to use MHD Valdez in the future for studying cell stability. But still, there's the issue about the friction coefficient that would require a squeeze test. Thank you very much for your attention.
Any questions?非常感谢您的报告 ，Mark。我相信你们在建模的时候是用了参数性几何，我。
No, I assume that the MHD Valdez has the construction method of the geometry and the mesh is parametric. So you define the cathode size, collector bar size, etc. And it controls the construction of the geometry mesh is automatic.
Yeah. No, but
Can you confirm this? And
what is parametric is the anode side, yes, and the position, the center channel, all those things. The same thing for the cathode, the size of the bar, the size of the cathode block. But what is not parametric is the bus bar layout, of course.
Yes, I understand. And what about in the case you have copper inserts?
It is now included as an extra input, so it is also parametric.
And in the case the copper is round or is on the top of the bar, you can manage this?
No, those are lines, so you care only about section.
It's about section, okay. But if it is in the top of the collector bar or in the middle, it's the same thing?
Good question. I think it must be parametric. I've not used that much copper insert, but it is an input, so yes, the position is relevant. So yeah. So I cannot confirm 100%, but it might. And also now the new version, you can define the temperature and the collector bar inside. So yeah, the code is evolving and is getting better to compute horizontal current, cathode voltage drop. That was not the main goal of initially, it was stability, but those things matter. So that's why this paper is to confirm that the code is doing a good job to compute those things.
Okay, thank you.
Thank you very much for a very good presentation, Mark. I'm just wondering if you are now looking at these high amperage cells like 600, 700, 800, what kind of modifications do you need to do with your model when you are doing, what kind of considerations do you have to take when you are...
There's nothing special to do. You input the size.
So you just change the size of the...
Okay. Yeah, you define the amperage, you define the size of the anode, the number of anode, the number of cathode block. So you can build a very small cell or a very big cell. I publish a paper where I have a 1 million amp cell in MHD Valdis, or you can go, the 3 met cell is 180 kiloamps, so there's no, any size will do.
Okay, yeah. Okay, thanks.
Lunchtime, huh? Yeah.
Yes, sir.
OK，再次感谢。
Okay, thank you. Thank you, Monsieur Dupuis. Thank you. Merci beaucoup pour la présentation. Merci.